Okay, so let's start with some basic physics tools. That's probably too small, right? Okay, so some basic physics tools. Okay, the first thing is work. So a lot of these problems will have to do with work. Okay, and so our general formula for work is, in mechanics, force times distance. Okay? Yeah, but that's if you have a constant force over a straight line distance, right? So if the force remains constant and you go in a straight line, or so you know exactly the length that you go, then it's just as easy as force times distance. Okay? But what if the force is variable? So what if the force as you're moving this thing over a distance, what if the force varies as a function? Well, then you can't use this, okay? So in that case, how will we calculate the total work? So if force varies according to a function, for example, how are we going to find the total work? How are we going to get the total work? Yeah, good. So we're gonna get little amounts of work and do what with the little amounts of work? Add them all up, and how do we do that? Integral. That's what integral does, right? So it's going to be integral of little bits of work. A little bit of work. Okay, and so that might be, so that we could say like dW, right? So dW is a little bit of work, and then we're gonna get a typical amount of work, and then we're gonna add up all the little bits of work. So that's the idea here. Okay, so work for spring is a little bit different. So springs, the force required to stretch a spring is the spring constant times the displacement. Okay, so force to hold at displacement x that's F, okay? And then x is, this is this displacement from its natural length. X is the displacement from natural length. And then k is the spring constant. So that's it's constant for a particular spring, and it's basically relates to how stiff or how loose it is. So if it's a strut on a car, it has a very high spring constant, right? So like what your shock absorbers in your car has a very high, like you couldn't budge that with your own arm, with your own hands, right? You couldn't even move that. But if it's a slinky, right, then it has a super, super low spring constant because it's just like there's absolutely hardly any resistance to it at all. Okay, and then everything in between. Okay, so now this displacement from its natural length. So when it's not being stretched or compressed, it has a natural length. And then so the amount that it's stretched from its natural length is x. Okay, so so what happens? The more that you stretch it from its natural length, the more force then it takes to hold it at that position. Okay, so this will be what? This will be the force part of the work. So we want the work then to stretch a spring. So the force is going to change as you're stretching it, right? So at first the force will be smaller, and then you move it a little bit, and the force will be a little bit bigger, and then so the more that you stretch it out, the more that the force will go up. So you're going to have to calculate a little bit of work for just stretching it a little bit. As soon as you stretch it, the force changes. Okay. So we'll see examples of that. Okay, so spring constants have units of, my notes are too small. So newtons per meter, that would be metric, or like pounds per foot, English. And so remember, so just remind you, force units. So our force units, newtons in metric, pounds in English. Okay, next. So let's talk about force. Metric versus English system. So some of the problems you'll be given will be in the metric system, some will be in the English. And there's kind of of course the units are all different, but then the approach to these, there's kind of something that's different about them. Okay, so, and what is force? Force is, so we know spring force, we know is K times X, we just talked about that. But any force, so force is what accelerates an object. Okay, so force is just generally defined as a motion that puts an impact or something that puts a object in acceleration. Okay, so it's m times a. Now, but that's really only used in English, this is really usually for metric only. Because when you talk about English, this is metric only because, so why is it metric only? Because in metric system, we consider the mass of something, right? So the mass in grams or kilograms. But in English units, mass is measured in something that's kind of obsolete and not really used. It's called slugs, okay? So slugs are the English unit for mass, but it's just not really used. So when you're working in the English system, you just work in force units of pounds. You don't really work in mass units the way you do in the metric system. So, but this is how you would get in the metric system, given the mass, how you would get to the force unit. You would use m times a. Okay, so masses in grams or kilograms. A is the acceleration of gravity, or is the acceleration, whatever the acceleration is. Okay, so we're not talking about in meters per second squared. And then therefore, NF is the force in newtons. Which is kilogram meter per second squared. So we're just laying some groundwork here. Okay, so for weight force, then so weight is a force. Okay, weight is the force of gravity on an object. Okay, so weight is a force, and so for weight force, it's the same thing except now the acceleration is the acceleration of gravity. Okay, and so then so you're going to use this mostly, you're going to have this in the metric system, because if they give you the mass and you need the weight will be in force units newtons. So you'll need G, which is 9.8 meters per second, 9.8 meters per second squared. Every second, a falling object speeds up by 9.8 meters per second. The speed increases not by 9.8 meters per second every second. Okay, so what else do we need here? So in English, it's 32.2 feet per second squared. So weight again, so we said this before, but so weight in the metric system is newtons. Okay, weight, it's not kilograms. What is kilograms? Mass. It's different. Mass is the amount of stuff. It's the same on the moon, in outer space, on Jupiter, on the Earth. Okay, but weight is a gravitational pull on the mass. So that changes depending on your gravitational field. Okay, so the weight on Earth is more than the weight on the moon, which is less than the weight on Jupiter, and then the weight in space is 0. Okay, so weight in the metric system is newtons, and then in English system is pounds. Okay, so in the English system, normally you'll just be, if you have a problem that's revolving around the English system, you'll just have the weight of the object, pounds. Lots of times in these metric problems, they'll give you the mass of the object, so you have to do an extra step. So your extra step would be, given the mass of the object, you're going to multiply it by 9.8, and then you have weight in newtons. Does it make sense? So there's that so that's what's confusing to a lot of students, because you're looking for this parallel method of doing this problem versus this problem, but this one's in English and this one's in metric, and the one in metric, there's something different about it, because if you're given mass, you need to convert that to newtons. Whereas if in the same problem in the English system, you'll just have pounds. You don't have to make that conversion because newtons and pounds are apples to apples. Okay, I hope that makes sense. So we'll see that though. Okay, so let's start with, we'll go back to springs here. We have room for it. So, let's not do that. Okay, so here's an example. All right, so we got force of 40 newtons is required to hold the spring too small. Force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to 15 centimeters. How much work is done in stretching the spring from 15 to 18? Okay, so if we're going to do this problem, we need to know what the spring constant is. And that's what that first piece of information is for. So the force of 40 newtons is required to hold a spring that's been stretched its natural length from 10 centimeters to 50 centimeters. That piece of information is to get us the particular K value for this spring. Okay, so how would we solve then for K? So we know the relationship is so F equals Kx, and 40 is required to stretch the spring what amount of displacement? 40 centimeters, if I wrote it down right. No, I don't know where I got that. 10 to 15, not 50. It's my bad eyes. Sorry. Okay, this makes more sense. Okay, so what is x? So the natural length is 10. We stretched it to 15, and now we're holding it there, and it takes 40 newtons. So we can go two directions with this. We could change this centimeters to meters and work all in newtons and meters, or we can stick with centimeters, and then we just know that our spring constant K is in terms of newtons and centimeters. So let's just do the second version. So either will work as long as you just keep your units consistent. We'll go with centimeters and newtons. So K is 8 what? Newtons per centimeter. So that's the K for the spring. Okay, so we got the natural length is 10. Okay, and then we're going to stretch from 15 to 18. So I'm showing it on the way, right? So I'm showing it as we're stretching it somewhere in the middle. So the natural length is 10, and we're going to stretch from 15 to 18. So how are we going to figure out how much work it takes to do that? Because as soon as you stretch it a little bit further, it's a bigger force that you have to pull against. So every time you move it a little bit, your force gets bigger. So what are we going to do? We're going to do a typical amount of work. So what will the typical little amount of work be? So think about, we're right here, and we're just going to go a little bit further, right? We're going to go a little bit further. So how much is that? How much are we stretching it? How much are we stretching it? If we're just going to go a little bit further, where this is what? From here, starting at 10, this is x. So it's going to be delta x. If we go just a little bit further, that's going to be delta x, right? And so that's going to be how far work is. Oh wait, so work is force. So work is going to be force, the current force times distance, a little change in distance. We can only go a little change so that the force is essentially constant for that little change. Okay? And so then what is the force at some value of x? Well, it's going to be 8x. Right? Because the force for the spring constant is 8, so the force is going to be 8x. And then the work at that force is going to be that force times the little distance that we go. Force times distance. And so that's going to be our little delta W. And so now the total work to stretch from 15 to 18 is going to be, we're going to add up all these typical amounts of work starting at x equals. I heard 10 and 15, neither of which are correct. What does x stand for? Displaced amount. So we're going to start from x equals 5. We're going to displace it from 15 centimeters to 18 centimeters. So the displacement, it's starting at a displacement of 5 and ending at a displacement of 8. Because remember, x is the displacement. And then we're going to add, from 5 to 8, we're going to add up all these little bits of work. Force, 8x, times distance. So do all our units correct. 5 and 8 are in centimeters. That's centimeters or newtons per centimeter. Okay, so super easy integral here. Four x squared. Let's just finish it out here fast. So it's going to be 4x squared from 5 to 8. And so that's going to be 64 times 4 minus 100. Is that 156? So what is our units? Our units of work would be force times distance, or newtons times centimeters. So here would be a good time to change it to newtons times meters. How many meters is 156? 1.56 Newton meters. And a Newton meter is the same thing as a joule. So Newton meters, 1.56. Very easy example to start with. But the principle is important, right? And it's the same principle we've seen over and over again. Find a little little piece of what you want the total of, and then use an integral to add them all up. Add them all up. So we got a typical piece of work. We're going to add them up from 5 to 8. Please.
Is that 64.4 minus 100?
I think so. Did I do it right? Times 4. Times 4.
You're right.
60. So 8 squared times 4 minus 25 times 4. Yeah.
Why is x from 5 to 8?
Because x is the displacement of the spring. Okay? X is the displacement. The natural length is 10. Okay? So when you stretched it 15, when you're stretching the spring from a length of 15 to 18, the displacement is from 5 to 8 because its natural length is 10. Is it better? So all that x is always the displacement from natural length, not length. It's not length, it's how far you stretched it from its natural length. But yeah.
When you're going from Newton centimeters times Newton to Newton meters, wouldn't it? I gotta confuse. Would it go the other way? Would it make it 156,000? Yeah, but if it's
No. So if it
what is Newton centimeters? Like what?
that's the work unit. So it's like how can we think about this? So it's like this is equivalent to doing 1 Newton of work over using 1 Newton of force over a distance of 156 centimeters. That's the equivalent. Okay. So then how many meters are you going? If you're going 156 centimeters, you're going 1.56 meters. So it's the equivalent of doing 1 Newton over 1.56 meters, which is the same as 156 centimeters. You see? Yeah. Yes, sir.
My question is, so right where your analysis, for your F, which is your force, when you plug in the 8x, can you just explain that? So I thought our force was 40 newtons.
No, 40 is only to hold it at 15 centimeters.
Right, that makes sense.
So the force of the spring is kx.
Yeah.
So the force to hold it is kx. So that's 8x because we found the spring constant was 8,
Yeah.
and there's x. So that's the force 8x. And then to get work, it's force times distance. Force times distance. So force of the spring to hold it displaced x times the distance gives you a little piece of work.
Thank you.
Yep. Okay, new example. Can I erase? Okay, so now we got a different type of example here. Wow, really small. So a 20 kilogram chain hangs 30 meters from the roof over the side of a tall building. How much work is required to pull the entire chain up to the roof? So we need a good picture here. So we got this building. Okay, and then picture. So then the chain is hanging down like this. and we're going to say X is positive this way from the roof, okay? So X is the distance down from the roof. Distance down from the roof. Okay, and originally it's 30 meters. So now I'm showing it partially lifted right now. Okay, so what we want is a little bit of work, right? So we're gonna so X is, let me just show it. So this is the chain. Currently, there's X meters left of the chain, right? So it started here. Originally, it was hanging all the way down to here, 30 meters. Now there's X meters left. And so we want the work. We want a little bit of work, what? To raise it a little bit, right? Because what happens as soon as we raise it in a significant amount? What about the force now required to keep pulling it up? Less. So the more that you pull this thing up, the more the chain is up on the roof, and the less force or weight is hanging down. So that's why you need little bits of work added together. Okay, so we're gonna have force times a little bit of distance, delta x, is a typical amount of work. So like you think of maybe like to pull it up one link, right? To pull it up one link, a little change in x. So what do we need? We need the weight of x meters of chain, because that's what the force we have to pull up with. So this is the weight of x meters of chain. Does that make sense? And we're gonna pull that weight a little bit, and that over that distance, and that will give us the work, that weight times that little bit that we pulled up. Okay, so what is the weight? We got a 20 kilogram chain, so the weight F equals mg, right? Or 9.8 times m. So the whole chain is 20 kilograms. How much does x meters? What's the mass of x meters of it? Yeah, so it's the weight or the mass of the chain depends on how much is still hanging over the edge. Okay. So what we really need is we need to know what its weight is per unit of length. That would be helpful, because if we had x meters and we knew how much its weight per meter, then this would be easy. Okay. So let's talk about what's the total. How about the total weight of the chain first? That's force, right? The total weight is the force, would be 20 kilograms times 9.8. So what's the total force of the chain? 196 newtons. That's the total weight of the chain. And how long is the chain? 30 meters, so 196 over 30. Let's get a number for that. What is that? 6.53. That's the weight per unit per meter. So this 20 kilogram, 30 meter chain, every meter weighs 6.53 newtons. So then how much does x meters weigh? We don't need this mass anymore. We took care of the mass over here. Okay, so what we need is the weight of x meters of this chain. How much does x meters of this chain weigh? 6.53 x. It weighs 6.53 newtons for every meter, and we've got x meters of it. So that's the weight of x meters of the chain. And how far are we pulling it up? Delta x, a little, we're just going to move it up a little bit. And that's going to be our a little bit of work. When x meters is hanging over the edge, the little amount of work you have to do to pull it up a little bit is its weight, or the force, times the distance. So now we're going to sum all those up. So this was our setup work here. We'll do it in blue. So now the total work is going to be integral. So x goes from what to what? 0 to 30. Of the little bit of work that we do at every length x. 6.53x dx. So two really easy ones to start. Those are easy, okay? Really easy. But we're just getting the feel for what this is like. So what are our units? I got newtons and meters, so this will be joules. So answer, I got all newtons and meters, so we'll get newton meters, and whatever comes out to be will be joules. Questions on this one? Okay. Harder. Can I erase? Okay. Harder and more to write. Okay, so now at 20. Hangs 30 meters to the roof. Start is the same. The chain has a bucket of sand that's spilling at a constant rate, such that at the initial mass of the bucket and the sand is 25 kilograms. Okay, so the initial weight of the bucket and sand (25 kilograms) and the 5 kilograms. That's mass. Okay. So this is harder. This is more typical. So not only do we have the chain, which is changing, its weight is changing as we get more and more of the chain on top of the roof, but now we've got this bucket, and it's spilling sand, and that's changing as you go up. So here's the key to this and many problems. So first of all, a picture. Okay, we want to get a picture. So again, same building, same chain. So our x, again, is going to be the same x. Okay, but we want to look at the mass, say, along the way. Okay, and so say x is currently like this. There's our bucket. Okay, here it comes. It's spilling sand. So at 30, down here at the bottom, when x is 30, what is the total mass of everything? What is it? 45. So when x is 30, or before we've started, the mass is 45, okay? And then when we get up to 0, what's the total? This is the total mass, chain, bucket, and sand. How much? How much for the chain? For the chain, when I get to the top? 0, right? We got all the chain to the top. And the only thing that's left at the very top is the bucket, and if there's any sand left, but they said that total is 5. So it's right before you get to the top, just before you get to the top, you're pulling up that last little bit. You're pulling on a mass of 5 kilograms. Okay, so what we'd really like to have then is, what is the mass at, so here's x, right? Right now, this could be any place, x. What's the mass at when the bucket is x meters below the top of the roof? Can you do it? So I've structured this very conveniently for you now to apply pre-algebra? Algebra? Before pre-calculus, that's for sure. So can you figure out the total mass at a length of x? At a length of x. If at 30 it's 45 and at 0 it's 5, can you figure out what the mass is when it's x? So I'm going to start taking attendance. That's your goal. That's your goal. What's the mass when it's hanging down x meters? Okay, so one thing that might be helpful is you could write ordered pairs. And what kind of relationship do we have between x and the total mass? Linear, right? So we know that the chain will lose its weight linearly, and it said that the sand is pouring out at a constant rate. So this is a linear relationship, and this is going to be in all these problems, these physics problems, is going to come up over and over again. Your ability to see that you have to come up with a linear relationship and then know how to do it. So you have to anticipate or identify when you have this kind of situation, and then be able to write a linear relationship. So we basically want with the mass in terms of x. So maybe so you can think of as mass as a function of x, okay? But that's going to be linear, right? So that's going to be a linear relationship. This is all over these problems. But you're the one who has to kind of set up the information in such a way that you understand it that way and then can do it. So there's lots of different ways. We could, my inclination is to get the constant rate first. So what is the constant rate of mass with respect to length? How would we do that? So that's like this, like m. Right? In the linear relationship, it's like m, not for mass, but so what would it be? It'd be the change in mass over the change in distance, which is, so you do 45 minus 5 over, and what's that? 4/3.
Should it be the other way around because both values are decreasing?
What's that?
Should it be 5 minus 45 because it's going from 45 to 5?
Okay. And then 0 minus 30?
Oh wait, never mind. That has negative
Yeah,
half.
yeah.
Yeah. Range.
Okay, so it's 4/3 what per what? Kilograms per. So this is basically how much you're losing, what the amount of mass you're losing per meter. All right, now what do we need? So there's different ways to set up. So this is basically the equation of a line, right? We're doing the equation of a line. So you can do point slope form. Here's one way to do it. So if you have your own way, that's fine. But point slope form is one way. Y equals m x minus x1 plus y1. There are other approaches, but this is one way to do it. So m is 4/3, and then we just need a point. Use the easier one. 0, 5. So our rate of change is 4/3 x plus 5. So this gives the mass at any length x. 4/3 x plus 5. And then you can check it. So instead of going to your teacher and saying, is this right? You can say, oh, look, if x is 30, do I get 45? So let's put in 30. 30 divided by 3 is 10 times 40 plus 5. Did it work? Yeah. Yep. And then I come to this one. I say, if x is 0, do I get 5? Yeah. Then you know it's right. So just once you get your relationship, then test the 2 points that you have. And if plugging in 30 gives 45 and plugging in 0 gives 5 and it's a linear relationship, boom, you're done. You got it. Okay, so can you finish the problem now? Can you finish? So now you know that the mass at any x, when the bucket is x meters from the top, the mass is 4/3 x plus 5. That's the mass in kilograms. So can you finish? Go, see if you can finish. Go, finish. Sorry. Yeah, so what does this say? This says when you have x meters hanging down, there is still this much kilograms.
No, I mean, what was supposed to do? Just that part. Before you said go ahead.
Right, so you're going to finish the problem. You're going to find how much work it takes now to raise this thing up. How much work it takes to raise it up. You got to be able to do this, so you might as well start now. Don't say I'll figure it out later. That's a recipe for disaster. So there's your set. There's your. It's easy from here. If you can't do this, you're going to be dead. So it should be easy from here based on the examples we've done.
That's included in the weight. Like this is article. That's just
I'll take one round for questions if you want to ask me a question while you're working.
not just no, because the chain is 20 kilograms, and then the bucket is 65. So that's how you got the chain. So this is the mass that you and shipping mass would be 2/3 of the weight and 1/4.
X is hanging down and the mass is 4/3 x plus 5. Okay, so if the mass is 4/3 x plus 5, then what's the weight at x meters? What's the weight? It's going to be our 4/3 x plus 5, right? That's how much mass you have, times. So that's the weight of x meters when x meters is hanging over the edge. That's the weight when, or the force. M times G. M is changing. It's according to x. M is variable. According to what x is, this is your mass. So your weight force is changing too. It's that thing times 9.8. So now we're ready to write typical amount of work. A little delta W is going to equal the force at x meters times the little amount of distance you're going to pull it, right? Work is force times distance. What distance are you going to move it? Delta x. You can only, so you're considering a constant weight for a little change in x. As soon as you move a significant change in x, the weight is different. It's going to be less. So you need a little change in x. And so then the total work is integral from 0 to 30, 4/3, so dW basically. So this is our dW. So it's summing up all the little bits of work. Okay, so what's this should have been the easy part. Okay? So here's the key to so many of these problems, whether it's emptying tanks, we're going to do emptying tanks, we're going to do hydrostatic pressure on the side of underneath a vertical wall, we're going to do raising buckets. But so many of these problems, it's identify and create we're not done. Identify and create linear relationship. Like we did at the beginning. So you have to recognize that you need to do that. You need to organize the information for yourself so that you're able to then write, in this case, distance or the mass as a function of how much chain is hanging over. And then from there, it's easier, right? So that's kind of the hard part of this problem. Okay. Any questions on this example? Okay. So new stuff here. So I mentioned emptying a tank. Let's do that. No.
Yes.
Friday. It'll be due Friday. All right, removing. So it's usually water, but it might be oil or chocolate milk or whatever. So density of. So we need some setup here. Density of water. 1,000 kilograms per meter cubed. Okay, so here's this thing again. So the density of water is given as 1,000 kilograms per meter cubed, or 62.5 pounds per foot cubed. So this is going to be the same situation again, because what kind of density is 1,000 kilograms per meter cubed? Okay, metric, but what kind of quantity is it? That's mass density. Mass density. And so 62.5 pounds per foot cubed is weight or force density. So this is apples and oranges. They're both the density of water, but they're not the same. So you're going to have an extra step if you're in the metric system, and you got to convert the density of water to what? To weight density. So we can just do it right now if you want. So what is it as a weight density? If it's 1,000 kilograms per meter cubed, then what would it be? Yeah, so it would be times 9.8 to get newtons. So it would be 9,800 newtons per meter cubed. So now, the 9,800 number and the 62.5, those are both weight densities or force densities. Those are apples to apples now. So you just have to be aware of this, because this. So in your English problems and your metric problems, you might be given kilograms in one, mass in one, and pounds in the other. That's not the same. You have to do something different in those two problems. Okay. So then the total, just as an example, the total weight of an amount of water So if we were in English, it's going to be 62.5 times what? What would you, 62.5 times what will give you the total weight of the water? The volume in feet cubed, right? That's going to be the volume in feet cubed. Because every 1 foot cubed weighs 62.5 pounds. So you're going to multiply the volume, whatever number of feet cubed you have, you're going to multiply by that by 62.5 to get the total pounds. Okay, so let's do one easy example here. A circular above ground pool has a diameter of 20 feet and a depth of 4 feet and by request, and is filled with chocolate milk, which has a density, I don't know, I'm guessing, let's see, what are we in here? So if we got feet, so 74.3. You guys can look it up later, but that's what I'm guessing. Okay? A little bit denser than water, right? Probably more. It's probably more than that. It's probably, let's do 94 point. Let's do 84.3. There we go. Okay. Real chocolate milk. Okay. Okay. So how much work is required to remove all the chocolate milk from the pool? Okay, so we've got the pool here. I have blue for water. I do not have brown. We'll just stick with black. Okay, so again, x is going to be down from the top. So why do we need integral for this? Why can't we just do work equals force times distance?
Because the mass changes as you take it out.
Nope, not quite. So we know work equals force times distance. So what's different? The distance, right? Like vertically, right? So taking the milk out from the bottom of the pool is going to take more work than the milk at the top, near the top, because we have to move it a further distance. Okay? So therefore, what is a little bit of work going to look like? So what's changing here is distance from the top. So we can take what is our typical element going to be? So our typical element of work is going to be based on what? In 1 minute. So we need some amount of milk that we can calculate the work for, so that the distance is the same and the force is the same. So how can we grab some element of what will the element of milk be like that for that whole amount, the distance will be the same and the force will be the same. Can you imagine it? So can I do like a vertical pillar of milk? Is that has the same distance for all the milk in there? No, because down here it's going to take more work than up here. So that's not our element. So what kind of element? Yeah, okay, so you're saying. So I'm going to do blue. So it's blue chocolate milk. So yeah, so a pancake. A pancake of milk will have all the same distance. Okay? So we got to move, what is the weight of a pancake of milk? Well, it's going to be the volume, the force is pi r squared delta x, volume times what? Density. 84.3. So that will be the total pounds. And so then the work to move that thing out, delta W, will be force times distance. The force is the volume times the density times what? Not delta x. It's now the distance we have to move that thing. Just x. X. We got to move it a distance of x. So now the delta x is part of the force. It's part of the weight. It's the thickness of our pancake of milk. And then the distance is no longer dx. The distance is x. The distance that we have to move that thing is x. Does it make sense? So the total work, and then we'll be done. Total work is all the we're going to add up all the work from each pancake. So it's going to be from 0 to, what's the depth? 4, 0 to 4.
We have to replace the radius by actual number. It should be 10.
Yes, thank you. So, yeah. So it'll be pi times, we know it's 10 squared, times 84.3, times the little thickness of the slab to get the weight. Right here?
You need an X in there after the 84.
Yeah, I need an X for the distance it's going. Thank you.
Will that X get distributed or no?
It's everything's multiplied. There's no everything's multiplied. There's no distribution. Everything's multiplied. Look on Blackboard for due dates, assignments. So like sometime tomorrow, I'll have the whole assignment laid out for you. I won't see you for another week. Be safe. Have fun. Be safe. I'll stay in for questions if you want. Where's the homework? Hi.
Hi, sorry, did you make a comment about the test? I thought I checked the schedule and have the test right after fall break. No?
No, the test. Where are the homeworks? Anyway, where did the homework go? It's really weird. Did I stick them in here? I'll stick them in here. Okay. No, the test is not till the Monday after next week.
Oh, okay. So we got it.
We have So we have a week from tonight, Wednesday, and then right now the test is scheduled for the following Monday.
All right.
So it's not next week.
All right.
Okay.